Electromagnetism, Lesson 4, Part A. So we're up to electromagnetic induction. So in this lesson, an electric current produces a magnetic field as it explained in the previous chapter and previous lessons. So a moving magnetic field can cause an electric current. This is called electromagnetic induction, and it's how most electrical power these days is generated, certainly if it's in large quantities. So for this lesson we're going to introduce you to a thing called the inductor, and we're going to do that using the textbook, chapter 12.1, 12.2, 12.3, Introduction, Electromagnetic Induction, and a thing called Lenz's law. So in about 1820, Oersted discovered the link between electricity and magnetism. In 1831, just a few years later, Michael Faraday found that a moving magnetic field causes a current to flow in a conductor. The effect, called electromagnetic induction, was studied by many notable people of the time, the names of which are now many of the units that we use in electrotechnology. So the first DC generator was produced about 1832, and today most electrical power is produced using electromagnetic induction. The only exception at this point would be solar, which uses photovoltaics, but wind, baseload steam generators, etc. all use electromagnetic induction. So let's have a look at how that happens. You can see here on our screen we have a magnet. I'll just turn my my screen pointer on, and we have a north pole, a south pole, and obviously the green is the magnetic flux, lines of flux passing from north to south. If we then move a conductor, which in this case is a brown wire, and we move it in the direction shown by the arrow, then we're going to get a couple of microvolts. You'll notice here it's microvolts. It's only going to be a tiny little bit of voltage for one conductor going through it. So a conductor moving in a magnetic field causes a voltage to be induced in that magnetic field, and just as the wire through the magnetic field is moving down, if I was to move it the opposite way up, then this meter would deflect the other way. So the polarity of the electrical current in the wire is determined by its movement and direction through the magnetic field. So again, reversing the direction, and you can see here we've now put the arrow going up and moving the wire up, and as I've just mentioned, the needle goes in the opposite direction, so the meter reads in the negative direction. So polarity, we call it, polarity is affected by the direction the wire moves relative to the magnetic field. Sometimes you might move the wire, sometimes you might move the magnetic field. In this case, we're moving the wire relative to the magnetic field. So this introduces us to what we call Fleming's right-hand rule. So if we use our thumb as the direction of motion, our index finger is the direction of the flux, and our third finger is the direction of the current. So Fleming's right-hand rule just gives a way of determining the direction of the induced current when a conductor is moving in a magnetic field. And again, in this particular case, the flux is moving north to south. We're moving the conductor up through the field, therefore the induced current is from the right to the left. So voltage induced in a conductor. The value of the voltage induced in a conductor is proportional to. So proportional to means it gets bigger as the
relevant thing gets bigger, so the length of the conductor in the magnetic field. So the more conductor you have in the magnetic field, the higher the induced voltage and therefore the induced current will be. 2. The speed relative to the movement between the conductor and the magnetic field. The faster you move it, the larger will be the induced voltage and therefore current. 3. The strength of the magnetic field. So the more lines of flux, the higher the density of the field. In other words, the more Teslas we have in the magnetic field, then also this will improve or increase the voltage and current in the conductor. It's also affected by the angle at which the conductor passes through the magnetic field. This is assumed to be a right angle at 90 degrees, but with rotating magnetic fields, as you will find out in AC eventually, it's not always the case. So the angle and the speed are actually interrelated to each other. So there's a relationship here between speed and angle. So as the angle gets shallower and shallower, the relative speed reduces. As the angle gets sharper and sharper towards 90 degrees, the relative speed increases. Therefore, the induced voltage will change. So speed and angle are directly related. So what if we want to calculate the voltage? The formula is E equals BLV, where E is the EMF, the electromotive force, measured in volts. B is the flux density, of course, measured in Teslas that we've already discovered. And L is the length of the conductor that is moving at right angles to the field, and it's measured in meters. So EMF is in volts, flux density is in Teslas, and L is in meters. And of course the final one is velocity, and that's in meters per second, both SI units. SI unit for time is the second, and for length is meters, so meters per second for velocity, being a measurement of speed, obviously. So here's an example. I've got a pole and it's got 110 millimeters wide. The flux density is 0.001 of a Tesla, and I've got the conductor moving away from me. So in this particular case, the velocity is 10 meters per second. The density is 0.001 of a Tesla, and the length is 0.01 of a meter, because 10 millimeters is 0.01 of a meter. Remember, our formula is E equals BLV, so we simply multiply the length by the Teslas, or the density, multiplied by the speed, in this case 10 meters per second, giving us 0.001 of a volt. Or we could express that as 100 microvolts just by moving this point 6 places to the right. So inducing a voltage in a coil, which is the typical way we do it because it's a nice efficient way to get the magnetic field cutting as many conductors as possible at a time. So here we have, you can see let's turn my pen on. We have an obvious magnet. Here's our magnet. And you can see the North Pole just starting to go into the end, and the South Pole, and the big blue arrows indicating that we're moving from our right to our left magnetic field. And as all of that magnetic field cuts each of the turn-ins, and it's actually cutting each of the turns twice on either side, we have a whole heap of microvolts all in parallel to deflect the meter to the right. So the winding of the conductor into the coil increases its strength and therefore increases the induced voltages, because basically we're picking up the
microvolts in that coil, then the microvolts in that coil, and then the microvolts in that coil, and we're simply adding them all up. So that's what's happening. Each coil basically is a little induced voltage, all placed in series with each other, and they're all adding up. So, but even though we might have a magnetic field, we need to have relative movement between the magnetic field and our conductors. In this particular case, no movement. So no movement, no induced voltage. The magnetic field is static in relationship to the to our coil here. Therefore, there is no deflection on the meeting. A voltage is only induced in a coil when the magnet is moving, or the coil is moving in relation to the field. So there must be relative movement between the magnetic field and the conductors. And of course, now if I was to extract that same magnet out as it moved out, and again you can see we've got relative movement, but now in the opposite direction, so our blue arrows are now going the opposite way, and we're now moving left to right in this direction. Therefore, again, our magnetic field is cutting the conductors, but we're now getting minus microvolts, minus microvolts, minus microvolts. Again, all in series, but that just gives us a minus voltage in the opposite direction, which we can see here on our meter. So the polarity of the induced voltage reverses when the direction of the motion is reversed. So voltage induced in a coil. Faraday's law is another way to calculate the induced voltage, and that is E equals N times the rate of change of the flux, N being the number of turns. So let's look at that. So voltage equals N, change in flux on change in time. That's what the little delta symbols mean. It's the Greek symbol delta, means change in flux on change in time, where the induced EMF, the little lowercase e, equals the number of turns of the coil. The rate of change of flux is in Webers cut per second. And we won't jump away from that too quickly. So our change in Webers on change in time, we simply group that together. So change in Webers on change in time is this one. So the change in the flux in Webers cut per second. Per means to divide. So it's Webers divided by seconds. So here's another quick example. Again, we've got a magnetic field, this time moving right to left. And we've got 1,000 turns. We've got a rate of change of 0.0015 Webers per second. So E equals N multiplied by the rate of change of the flux. So we simply say 1,000 times 0.0015 because it's already in Webers, and we get 1.5 volts will be induced. So we now move on to 12.3, Lenz's law. So let's look at what Lenz's law states. The current induced in a conductor will set up a magnetic field that opposes the magnetic field that causes the current. It's very hard sometimes to get your head around that, so I'll say it again. This is Lenz's law. The current induced in a conductor will set up a magnetic field, and that field opposes the magnetic field that caused the current in the first place. So here's what's happening. As we're moving the conductor through a field, a magnetic field, a voltage is induced or a current then flows from that induced voltage, and that current itself also produces its own little magnetic field. That's what they're saying. Its own little magnetic field is produced. And that's what we have a drawing of here. So we have our main magnetic field running across here, north to south. Then as we move our move relative to our magnetic field, our conductor through it, and as it penetrates the magnetic field, a secondary magnetic field is established, and it opposes, it is opposite. It opposes, it's in the opposite direction to that which created it, and that's called Lenz's law. And it will play a very significant role when you move into alternating currents. So it's good to understand now what Lenz's law is, because it is going to play a significant role in further learning. So Fleming's right-hand rule gives us the direction of the induced current, and it flows, the current is flowing towards you, causing an anti-clockwise field around the conductor. The fields repel because their lines of force are in the same direction to each other. So instead of combining, they repel each other, which you can see here very clearly. They are wanting to push each other away, because field number 1 actually produced field number 2, and they are the opposite to each other, and this is called Lenz's law. So Lenz's law acting on a coil. So as the magnet is moved into the coil, the magnetic fields want to repel each other. So as we're moving from left to right, up here on this one we're moving in this direction. Once the magnet is inside the coil then produces its own magnetic field, which wants to then push the coil back out again. But as you then decide to pull the magnet back out the other way, the opposite happens. You get this force of attraction because the two magnetic fields align and want to go in the same direction. So Lenz's law, the coils of the magnetic field oppose the movement of the magnet. So oppose the movement of the magnet. In the top one, as you're pushing it in, it wants to push it out. As in the bottom one, when you pull it out, it wants to push it back in again. So that's Lenz's law. And I use this little experiment quite often to demonstrate Lenz's law to students. I get a little button magnet, and I put it inside a copper tube or an aluminium tube, and I normally drop a piece of iron through the tube and it drops straight through within less than a second. Then I get a button magnet. I drop the button magnet into the top, and about 3 minutes later, yes, about 3 minutes later, over about 2 meters, the button magnet eventually drops out the bottom, and the students are always astounded at what's going on. Well, what's going on is Lenz's law, and let me explain. So here's our magnet falling in this direction through our copper tube. So it's falling in this direction, and as it falls, it has these magnetic fields. The red loops are the magnetic fields of the button magnet, and of course those fields are cutting the copper of the tube, which is a conductor. As it cuts that tube, it creates a current that flows in the tube. You get a little current across the wall. Literally, you get a little current across the wall of the tube. That current across the wall then produces these yellow fields. So you get a yellow field being created, but the yellow field are opposite to the red one. So these two here, guess what they want to do? They want to push each other away. So instead of the magnet falling straight through, the magnet creates two magnetic fields which are opposed to each other, and it wants to push the magnet back up in this direction. Of course, gravity's a little bit stronger than the magnetic fields being produced, but the magnetic fields effectively suspend the button magnet via its magnetic field inside the tube. So the button magnet floats effectively very slowly down the tube because of these two magnetic fields opposing each other as it passes down the tube. So that's a very strong demonstration of what we call Lenz's law, that a magnetic field produces another current in a conductor, and that secondary magnetic field opposes the one that set it up. So in this case, the red one, field 1, sets up and creates a current. Step 2 in the wall of the tube. Step 3, that current produces another magnetic field, and those magnetic fields are opposed to each other. They're wanting to push each other away, and that's what we call Lenz's law. So that brings us to the end of electromagnetism, lesson number 4. Hope you've enjoyed learning a little bit about electromagnetic induction and how it operates, particularly in relation to the right-hand rule and Lenz's law.